Welcome to the June 2025. This is paper 2 of the A-level, the Edexcel A-level series. All right, question number 1, straightforward factorization. I'm going to start by factorizing out 2x. So 2x, lots of x squared minus 12x plus 20. And that quadratic factorizes to x minus 10 times x minus 2. And I fully factorized. Question number 2, fairly straightforward integration. So add 1 to the power divided by the new power. X to the 4 integrates to x to the 5 over 5, or a fifth x to the 5. Add 1 to a half and you get 3 over 2. Divide by 3 over 2. It's the same as multiplying by 2 over 3. Integrating negative 3 goes to negative 3x plus the constant at the end. So 1/5 x to the 5. The middle bit simplifies to minus 4x to the 3 over 2 minus 3x plus c. Question 3, we need to take logs of both sides. It doesn't matter if you want to take natural logs, if you want to do ln of both sides, or if you want to do log base 10 or log base 3 or log base 7. Any of these ways, I've done natural logs here. Any of these ways will be fine. We can apply our log rule to bring the power down on both sides, divide both sides by y, divide both sides by, in this case, ln 3. So ln 7 over ln 3 is what we're looking for. If you had log base 10 of 7 over log base 10 of 3, that's fine too. All right, question number 4. We can use the cosine rule to find the missing angle. That's on the triangle ABD. So the angle finding version of the cosine rule will be cos of A equals B squared plus C squared minus A squared over 2BC. Inverse cos of both sides, and we can jump straight to the angle. So our angle here will be inverse cos of 8 squared plus 13 squared minus 6.4 squared all over 2 times 8 times 13. And that comes out, of course, as 0.394 radians. And to find the shaded region R, we find the area of the triangle ABD and then subtract the area of the sector ABC. So the triangle, I'm going to use half AB sine C, half times 8 times 13 times sine of 0.394. And I'm going to subtract theta over 2r squared. That's 0.394 over 2 times 8 squared. And plugging all that in, we get an area of 7.36 centimeters squared for B. Question number 5, parametric equations. We know the x-coordinate of P is negative 3, so I'm going to substitute that into the x equals t minus 1 over 2, so negative 3 equals t minus 1 over 2, multiply both sides by 2, add 1, and we get that t at this point, our parameter is going to be negative 5. We can take our negative 5 and plug it into the y coordinate, so y will be 5 lots of negative 5 plus 2 to the power of 4, which is 405. For B, to find the Cartesian equation, I'm going to make t the subject of the equation with x. So to do that, times both sides by 2, add 1 to both sides, we get t equals 2x plus 1. Then taking that and plugging it into the equation with y in, replacing t with 2x plus 1. Y equals 5 lots of 2x plus 1 plus 2 to the power of 4, and I'm just going to simplify that, so 5 lots of 2x plus 3 all to the power of 4. And there's a Cartesian equation. For C, I'm going to differentiate that. I'm going to use the chain rule. It's perfectly possible to differentiate the parametric equations if you want to do it that way. Either choice, absolutely fine. I'm going to use the chain rule to differentiate what's in front of me. Differential of 2x plus 3 is 2. And then times by the 4 and subtract 1 from the 4. It comes out as 40 lots of 2x plus 3 all cubed. To find the gradient at that point, we're going to substitute x equals negative 3 in. So it's 40 lots of 2 times negative 3 plus 3 is also negative 3. So 40 times negative 3 cubed, which comes out as minus 1080 for the gradient. Question number 6. So we're dealing with the small angles. Cos of theta when theta is small is 1 minus theta squared over 2. That's our approximation. So replacing theta with 2 theta, or 2x in this case, our 1 minus cos squared 2x becomes 1 minus, and then it's 1 minus 2x all squared over 2, and then all squared. So that's going to be 1 subtract, and then 1 minus 2x squared. I'm just simplifying everything down inside the fraction, and then expanding that out. 1 minus 4x squared plus 4x to the 4. The ones cancel, and we get 4x squared minus 4x to the 4, which is what the question wanted. For part B, using the small angle formulae for sine and tan, basically sine theta is approximately equal to theta, tan theta is approximately equal to theta. We can replace sine of x over 3 with x over 3. We can replace tan of x over 2 with x over 2. And that gives us a little algebraic fraction we can simplify. X over 3 times by x over 2 is x squared over 6. And dividing by x squared over 6 is the same as multiplying by 6 and dividing by x squared. And so that all comes out nicely as 24 subtract 24x squared. Now for part C, 24x squared is approximately equal to 0 when x is very small, because you square a very small number and it becomes even smaller. And so 24 subtract a number very close to 0 is going to be equal to, approximately equal to 24, or as close to 24 as we would want. That's question 6 done. Question 7 is the massive partial fractions question. So as with all partial fractions, I'm going to start by multiplying both sides by the denominator, x plus 1 times x minus 3. So we're left with the numerator on the left-hand side, then it's going to be ax times by x plus 1, x minus 3. B lots of x plus 1, x minus 3. With the c term, the x plus 1s will cancel, so it will just be c lots of x minus 3. And with the d term, the x minus 3s will cancel, so we'll be left with d lots of x plus 1. Now we're going to just choose intelligent strategic values for x that are going to make a lot of things disappear. I've chosen 3 for the first one. It makes the a, b, and c terms disappear because of the x minus 3 that's next to them. That becomes 0. The left-hand side is negative 20, and we get 4 lots of d, therefore d is negative 5. Same strategy, x is negative 1. The a, b, and d terms will disappear this time. We'll get negative 16 equals negative 4c, so c is 4. And then it gets a bit trickier. I'm going to choose x to be 0. It's quite a nice number to plug in. The left-hand side is obviously negative 11, and we'll get negative 3b, subtract 3c plus d. On the right-hand side, we know what b and c are. We can substitute those in, and then solve the equation to deduce that b must be negative 2. And then the last option, I've gone with 1, because plugging 1 in is quite nice. You can choose other numbers though. Left-hand side's negative 22, we'll get negative 4a, subtract 4b, subtract 2c plus 2d. We now know what b, c, and d are, so we can substitute those in. and then bring everything together and solve to find a, which is 3. Question number 8. To show that a is negative 4, I'm going to take the equation where we know it's got a maximum at x equals negative a quarter, so at that maximum point the gradient will be 0. So if we differentiate our function, 4x cubed plus x squared, subtract 16x plus a. We can equate that to 0 when we substitute negative a quarter in. So 0 will be equal to 4 lots of negative a quarter cubed plus negative a quarter squared, subtract 16 lots of negative a quarter plus a. Calculate each bit of that. And we get 0 equals negative a 16th plus a 16th plus 4 plus a. Therefore, we can deduce that a must be negative 4. For part B, we now know that a is negative 4, and so we can just substitute negative a quarter into the original function along with our value of a to calculate the y-coordinates. So we get negative a quarter to the power of 4 plus a third lots of negative a quarter cubed, subtract 8 lots of negative a quarter squared, subtract 4 lots of negative a quarter plus 17 thirds, and that comes out as 4,735 over 768. And that is the y-coordinate of our maximum point. For part C, essentially we're working out the range of values of a straight line y equals something, essentially a horizontal line that crosses our curve at 4 separate points. So if we can find the y-coordinates of the maximum and the minimum, those are the two on the left, that will do it. Obviously there's 3 stationary points, so when I factorize our differential, equate it to 0, I'll get 3 points, but I'm looking at the 2 on the left hand side. So we already have the x is a negative a quarter, so the other one we want is when x is negative 2. When x is negative 2, plug that in, we get negative 5 out. So our maximum point, negative a quarter, 4,735 over 768, and then negative 2, negative 5. If k is anywhere between the 2 y coordinates, that horizontal line is going to intersect the graph at 4 separate points. So to write that in set notation, k is going to be a real number where it's bigger than negative 5 and less than 4,735 over 768, like so. All right, question number 9. We're looking at the value of a car. First thing we're going to do to find the total number of cars sold in the first 3 months, we're going to substitute t to be 3 into the model they've given us. So 5,000 subtract 5,000 lots of e to the power of negative 0.075 times 3. And that's equal to, when you plug it in, 1,007. For part B, I'm going to replace n with 3,000 and solve the equation. So 3,000 equals 5,000, subtract 5,000 lots of e to the power of negative 0.075 times capital T. I bought 5,000 e to the power of that stuff onto the left-hand side, subtracted 3,000 from the right-hand side, and then divided by 5,000. So e to the power of negative 0.075t is equal to 2/5. Take natural logs of both sides. We'll get a negative 0.075t will be equal to the natural log of 2/5, ln of 2/5. Dividing both sides by negative 0.075 enables us to find our value capital T, which is 12.22 months. The question wants it to 2 decimal places. For C, we want to find the rate of change. And so we're going to differentiate the equation, find dn by dt. The 5,000 will disappear because it's just a constant. To differentiate e to the power of kx, we just multiply by k. So in this case, we're multiplying by negative 0.075. 5,000 times that is 375. The negatives cancel. So we get 375 e to the power of negative 0.075t. Plugging t equals 3 into that differential, 375 times e to the power of negative 0.075 times 3 is 299. A few options for D. We can change our two constant values to 6,500. You could change one of them to 6,500. That would be acceptable. I've gone with both of them, 6,500 minus 6,500 e to the power of negative 0.075t. Question 10. Well, it tells us that the water is going in at a rate of 0.45, so dV by dt will be equal to 0.45, but then it's going to subtract the water going out, which is going out at 0.3V. So dV by dt will be 0.45, subtract 0.3V, multiplying both sides by 20. We'll get 20 lots of dV by dt, which will be equal to 9 subtract 6V. For B, we've got to solve the differential equation, so I'm going to divide both sides by 9 subtract 6V and separate the variables, separate the dVs and the dTs. Of course, not strictly mathematically correct, but it works. And we can integrate both sides now. So left-hand side will integrate to negative 20 over 6. You can simplify that if you want. Ln of 9 subtract 6v, and 1 will integrate to t plus the constant of integration c. Now, in the question it tells us when t is 0, v will be equal to 0.25, so we can use that to work out c. Substituting it in, we get c is equal to negative 29ths of ln of 7.5. Then we can now go back to the equation and plug that in. So instead of c, we now have subtract 26ths of ln of 7.5. If you simplified the fractions, that's absolutely fine. Then multiplying both sides by negative 6 over 20, we get ln of 9 minus 6v equals negative 0.3t plus ln of 7.5, or 15 over 2. I'm going to raise both sides of the equation to a power of e. On the left-hand side, that cancels out with a natural log. On the right-hand side, we'll get e to the power of negative 0.3t plus ln of 15 over 2. I've split that up and cancelled the e's and the ln's to bring the 15 over 2 down in front of the other e. And then all that remains is to rearrange the equation to make v the subject. And once everything's simplified, v equals 3 over 2 subtract 5 over 4 lots of e to the negative 0.3t. And that's in the form that the question wanted. For part C, well, looking at that equation, we're going to have 3 over 2, 1.5 is going to be a maximum value. You're only going to be subtracting something from that, so this container is never going to fill up above 1.5. So will it ever become full? Well, no, because it would need to be 2 or higher to fill up. So no, not in this case. All right, question number 11. So we've got a company trying to make a profit. We're going to construct a straight line here. So y equals mx plus c. We know that when the price of each toy is 30, we get 1,500. So 1,500 is equal to 30m plus c. When it's 50, we get 300. So 300 equals 50m plus c. And we can solve those simultaneously to find the gradient and the y-intercept. Whichever way you do that, if you do it correctly, you'll get the gradient to be -60 and the y-intercept to be 3,300. So the equation of our straight line here is y equals -60 x plus 3,300. All right, for part B, P is now being measured in thousands, so I'm going to stick 1,000 P at the front there. You could have dealt with that the other way, absolutely fine if you have. It's going to be y times x subtract 10 subtract 8,000, because you can take £10 off each toy and then subtract the 8,000 as the fixed cost. And that's going to give you the profit. So we're going to play about with this now. We know that y is equal to -60x plus 3,300 from part A, so I can substitute that in. Expanding it out, we'll get 1,000p equals -60x squared plus 3,900x subtract 41,000. And then the last step to find this in the form of p equals is divide both sides by 1,000, and we get the equation that the question wanted. All right, for part C, well, if they're going to make a profit, that our value of p must be greater than 0, so we can set up an inequality. 0 must be less than -0.06x squared plus 3.9x subtract 41. Solve the quadratic. If you solve the quadratic in any way you want, you'll get 13.19 and 51.81 if you do it correctly. And so x is going to be between those two values, because it's a negative quadratic. So it's an unhappy face if you want to visualize it that way. The maximum, because it is a quadratic, the maximum is going to be halfway between the roots. So I can add my 13.19 and 51.81 together and halve it, and we get £32.50. Part E, essentially we're just going to test out our model. So plugging 35 into our equation for the profit, we get 22,000. Now, the real life example was 21,750. It's pretty close. So that suggests that the model is a good one. Question number 12. For part A, we know modulo A is 1, so A could be 1 or -1. If I plug 1 into our function, we'll get 3 out, because the -2 becomes +2. And if I plug -1 in, we get 11 out. the negative 4 becomes positive 4. For part B, the range of f of x, well, we can see on the graph that minimum point at 3, negative 5. Everything's going to be above that, so f of x would be greater than or equal to negative 5. And if I take values that are greater than or equal to negative 5 and plug them into g, I'm going to get values that are greater than or equal to 7. So the range of the composite function is 7. For part C, I'm drawing two lines on to help us. That the range of values for k are going to be gradients in between those two lines. The gradient of the line that's parallel to the left-hand part of the modulus function is going to be negative 4, and the other line is going to go through the origin and have a gradient of negative 5 over 3. So whenever k is between negative 4 and negative 5 over 3, we'll get no solutions for any other gradients. The line will cross the function at least one point. So negative 4 is less than or equal to k is less than or equal to negative 5 over 3. Question number 13 is kind of a thinking question. For part I, well, we know that sine x is periodic between 0 and 2 pi. So if we have 6 solutions, then we must have stretched it by a scale factor of a third, so n's got to be 3 to get all 6 solutions. For part 2, this time we're running from 0 to 5 pi. By squaring it, it raises everything into the positive sort of quadrant, so everything is now above the x-axis. We're getting 6 solutions for every pi. We know that from part 1. And between 0 and 5 pi, we're going to have 5 of those intervals with 6 solutions in each. So 5 times 6 gives us a total of 30 solutions within that range. If you think about it, just bouncing on top of the x-axis, intersecting 6 times between 0 and pi, and then between pi and 2 pi, etc., all the way up to 5 pi. 6 lots of 5 gives us 30 solutions in that range. Question number 14 is the vectors question. We're going to firstly deduce that k is equal to 5. I'm going to construct the vector AB in an alternative way. To go from A to B, well, we get given it as 2A plus 3B, but I'm going to do it by going from A to D and then from D to B. A to D, we know is parallel to B to C, so it's going to be a scalar multiple of B to C, so I'm going to call that lambda B to C, and then D to B is subtract 4A plus K lots of little b. B to C we know is 15A, subtract 5B, so our lambda BC becomes lambda lots of 15A minus 5B. I'll leave the subtract 4A plus KB alone. And then if I expand that out, we're going to get 15 lambda lots of little a, subtract 5 lambda lots of little b, subtract the 4 lots of little a plus the k lots of little b. And then I'm going to factorize out the coefficients of little a and the coefficients of little b. So we got 15 lambda minus 4 lots of little a and k minus 5 lambda lots of little b. And if I compare that vector with the vector AB that we get given in the question, the 2 little a plus 3 little b, we can deduce values of lambda and therefore k. Okay, so coefficients of little a have to be the same, so 15 lambda minus 4 must be equal to 2, and therefore lambda must be equal to 6/15, which simplifies to 2/5. And then looking at the b's, we know that k minus 5 lambda must be equal to 3. We know that lambda is 2/5, so plug 2/5 in that k, subtract 2 will be equal to 3. Therefore k is equal to 5, which was what the question wanted. All right, for part B, we're going to find beta x in two different ways and compare them. We know that beta n is going to be 3 lots of little a subtract b, because b to n to n to c is 1 to 4, so it's a fifth of the length. So b to n is 3a minus b. I'm just going to park that there. Then the first way of doing b to x is a scalar multiple of b to d. I'm going to call that scalar multiple t. So t lots of b to d. B to d, the root from b to d is going to be b to a plus a to d. So that's going to be t lots of b to a is minus 2a minus 3b, and a to d is 6a minus 2b. So it's t lots of all of that. If I collect the a's together and expand it out, we get 4t lots of little a minus 5t lots of little b. All right, my alternative way of going from b to x is to go from b to a and then go a scalar multiple of a to n. I'm going to call this particular scalar multiple mu. You can call it whatever you like. So b to a is going to be minus 2a minus 3b plus mu lots of, and then a to n is going to be 2a plus 3b plus 3a minus b. And then if I collect together the stuff inside the brackets and expand it out, we'll get minus 2a minus 3b plus 5 mu lots of little a plus 2 mu lots of little b. And that factorizes to 5 mu minus 2 lots of little a plus 2 mu minus 3 lots of little b. And then I'm going to do the same as before. I'm going to compare the coefficients of little a and compare the coefficients of little b. For the little a's, we've got 4t, and then we've got 5 mu minus 2. And then for the little b's, we've got negative 5t and 2 mu subtract 3. We now have simultaneous equations, solve them however you like. I'm going to multiply the first equation by 2, the second equation by 5. So we've got 8t equals 10 mu subtract 4, and negative 25t equals 10 mu subtract 15. And we subtract the second equation from the first. 33t will be equal to 11. So t is going to be 11 over 33, or if you prefer, a third. Okay, so now we know that t is a third. Beta x, which is 4t lots of little a minus 5t lots of little b. Substituting in t to be a third, beta x is going to be 4/3 of little a minus 5/3 of little b. We know that b to d is 4a minus 5b. I'm going to factorize out 3 from that. You'll see why, because that's 3 lots of 4/3 little a minus 5/3 little b. Well, that's 3 lots of beta x. So beta d is 3 lots of beta x. So essentially, beta d is split up into 3 parts, all sized b to x. And so finally, the ratio beta x to x to d will therefore be 1 to 2. All right, for the integration question, part A, we're going to differentiate our function. So this is differentiating a fraction involving 2 functions. Simplest way is the quotient rule. You can do it by the product rule if you want to, but I'm going to go with the quotient this time. So my u and my v, my u is 1 minus x squared, v is 1 plus x squared all squared. Differentiate u, you get minus 2x. Differentiate v, we'll get 4x, lots of 1 plus x squared. That's the chain rule in there. So our differential f dash of x is going to be v du dx minus u dv dx all over v squared. So minus 2x times by 1 plus x squared squared. Subtract 1 minus x squared times by 4x and 1 plus x squared. And that's all over v squared. So 1 plus x squared squared squared. I enjoyed saying that. Okay, we want the stationary point, so that's going to be equal to 0. I'll replace my f dash of x with 0. That means I can multiply by my 1 plus x squared squared squared, and that will disappear, and we'll be left with just the numerator, which I'm going to start to tidy up. So we've got minus 2x, lots of 1 plus x squared squared, subtract 4x, lots of 1 minus x squared, 1 plus x squared. I'm going to expand out the 1 plus x squared squared, so it's 1 plus 2x squared plus x to the power 4, and then multiplying the 1 minus x squared by 1 plus x squared, we'll get minus 4x, lots of 1 minus x to the 4. Expanding all of that out, we'll get minus 2x minus 4x cubed minus 2x to the power 5 minus 4x plus 4x to the 5. We can now collect like terms, so we'll get 2x to the 5, that comes from the 4x to the 5 minus 2x to the 5, minus 4x cubed minus 6x. That's going to factorize. I'm going to factorize out 2x to begin with. So 2x, lots of x to the power 4 minus 2x squared minus 3. That's a disguised quadratic, so I'm going to factorize that. It's 2x, lots of x squared minus 3, x squared plus 1. X equals 0 is a solution there, but not interesting. That's the maximum point on the y-axis. X squared plus 1 is not going to give us any real solutions, so we're going to get x being plus or minus the square root of 3. We're interested in p, so that's the left-hand one of those, so the negative square root of 3. If I plug negative root 3 into the function, the original function, we'll get 1 minus 3 all over 1 plus 3 squared, which is negative 1/8. So our point P is negative root 3, negative 1/8. Okay, for part B, we're going to substitute x equals tan theta in to our function to help us integrate it. So integration by substitution, find dx by d theta, tan theta differentiates to sec squared. I'll treat dx by d theta as a fraction, not strictly correct, but we'll go with it. And then find out the new values for the integral. So we're integrating originally between -1 and 1. So when 1 is equal to tan theta, theta's pi over 4. When -1 is equal to tan theta, theta's negative pi over 4. So we get our new boundaries for the integral. Substituting x for tan theta into the function, we'll get the integral between negative pi over 4 and pi over 4 of 1 minus tan squared theta. And that's going to be over 1 plus tan squared theta all squared. Times by, and no longer dx, but sec squared theta d theta. That's going to simplify to, well, 1 minus tan squared is 1 minus sine squared over cos squared. 1 plus tan squared is the same as sec squared, so I can cancel one of the sec squareds with the sec squared theta on the right, leaving me with just 1 sec squared. Sec squared is the same as 1 over cos squared. So my integral becomes 1 minus sine squared over cos squared all over 1 over cos squared. If I multiply the top and the bottom by cos squared theta to tidy this up, well, the top becomes cos theta minus, and then sine squared theta over cos squared theta times cos squared theta is just sine squared theta. The bottom turns to 1, and so we get the integral of cos squared theta minus sine squared theta, which of course is the same as cos of 2 theta. And that's what the question wanted from us. Part C, integrating cos 2 theta, we get a half sine 2 theta. That's between pi over 4 and negative pi over 4, of course. Substituting pi over 4 into that, we'll get a half sine of pi over 2. And then substitute minus pi over 4 and subtract it, so minus a half sine of minus pi over 2. That's going to be equal to a half subtract a negative half, which comes out really prettily as 1, and that's the area under the curve. Well, I don't know if you got that. Bye.